Let's just start the record already, and I'll chop it later. So in case for those who are already here, I am recording the session.
So it says that the host has disabled participant screen sharing.
It's really weird because you're co-host. Oh, I made Larissa co-host. Oops.
I mean, Larissa can give the talk. That'd be fine.
You are now co-host. You should be able to share.
There we go. Yes, I have it now. Okay, can you see that?
Yep, it looks great.
Awesome.
I'm just seeing your PowerPoint. Everything's happy. I'm now setting up my screen so I can see what people say. If they ask anything. It's shedding season, so I've been petting my cat, and I'm literally covered head to toe in cat hair now because she's just shedding, and I think she's stressed because of the construction, so she's been hiding, so she's also like freaking out, having a trying day, setting, correction, she doesn't know what to do. I always find this wait quite awkward. I hate the Zoom wait. I actually think I just hate Zoom at this moment in time.
I agree.
I have friends who don't use it all day, and so they're like, "Ooh, let's have a little Zoom session." They're like friends from college, and I'm like, okay. I want to see you, I want to talk to you, but more time on Zoom is not my favorite thing these days. But they were very impressed with my power, right? Because I have a pro account.
Yep.
And they're like, oh, 30 minutes, it shuts down. And I'm like, not mine. Hey, Winnie. I have you logged, which I believe this is the second talk besides yours, or well, yours is on coming up, but your second talk, is that correct? Cade won the prize for being done. He's given his talk and he's attended 5. Hi. I don't know if you saw that, the cat hair fluff up. Shedding. They're too high? Hello, Mick. Mick, I have this as talk 4 for you. Alice Fleshman, do you need me to log your attendance in this session?
Yes.
I have you, Galini. This is talk 3 for you. Not including your own, of course. Evan, this is talk 4 for you. Frankly, this is talk 4 for you. 9. Aiden, this is talk 3 for you, not including your own.
Wait, our run doesn't count.
Was that something to me?
No, it's just a bad joke.
Okay. Elizabeth, I haven't logged you yet.
Sorry, what was that?
I'm logging you.
Oh, okay. Hi.
This I have as talk 1 for you.
That is true.
Perfect. Okay, so it is 4 o'clock, so it is the witching hour, I guess. We are in the 7th of our 20 talk series for our chemistry senior experience in chem and biochem. So I'm really happy to have you all join us as we go through these wonderful projects that each of our seniors are presenting. Just such a wide array of wonderful experiences and wonderful talks. I hope you will join me for talks next week, which are going to be starting on Tuesday at noon with Winifred Waters, and then we'll have a series on Wednesday afternoon and then Friday afternoon, giving a talk at 3:10 and 4 o'clock. I will be sending out an email. If you're part of the 680 class, you already have all the information and the Zoom link to do that. But if you're ever concerned of how to get there, feel free to send me an email. With that, I'm going to pass off the introduction for this lovely talk over to Allison Fleshman. So Allison Fleshman, take it away.
Go team! Well, it gives me great pleasure to introduce Katie Kitzinger, who comes to us from Newburgh, Wisconsin, although through Arizona. She was actually a transfer student from Arizona State, and thankfully she decided that Lawrence should be her home, because while she's been here, Katie's one of those fantastic students who challenges you because of her innate curiosity, and she understands chemistry, and if she doesn't, she asks you and she challenges you to understand it better. I helped her write, she did it all, an application for the prestigious NSF fellowship program, and she was awarded honorable mention in that, and I honestly forgot that I was working with a student when I was working with her. She's already a colleague. And it gives me great pleasure also to announce every year the chemistry department gets to select one outstanding senior. And so with unanimous vote, we've decided to award Katie the senior award for representing basically what a chemist should be in both spirit, academic rigor, and just pure kindness. So yay, Katie. And she did research with me, so it's even an ultimate bonus. So the work that she's going to present is, well, I'll let her tell you. But we hope to write a paper over her work over the summer before she heads off to North Carolina to pursue her degree in physical organic. I can't read words in front of me and say the things at the same time. Anyway, so Katie, go team, just go team. You're awesome. So awesome. To Katie.
Thanks so much, Allison. And thank you all for coming to my talk. I'm really excited to talk to you today about understanding ionic liquid viscosity, in particular the applications of the compensated Arrhenius formalism. So to start off my talk, I would like to first address what are ionic liquids, or ILs. And given that we tend to be more familiar with inorganic salts, I like to define ionic liquids by thinking about how they compare to this more typical material. So if we think about inorganic salts, we'll probably have this picture or something like it in our minds, where we have a large anion that has a negative charge, and that's going to be interacting with a small positive cation, represented here by the blue. Since these ions are symmetric, they can pack closely together, and they're going to have strong ion-ion interactions. So these materials are commonly solids at room temperature. Ionic liquids, however, are a little more messy. We see that we still have a solution of ions, so a cation and an anion, but our cations are much larger, and they also have some asymmetry to them because they have these nonpolar tails that are composed of carbons and hydrogens. Because of the larger size of the cations and the asymmetry in this system, these ions aren't going to be able to pack as closely or as regularly as the ions in an inorganic salt. And so they're not going to be able to interact as strongly, and these materials are typically going to be liquids at or around room temperature. Another thing to note about ionic liquids is that those nonpolar tails have interactions of their own. So when these tails get together and they cluster, they also stack and can have van der Waals interactions. So in addition to the ion-ion interactions happening, we also have those van der Waals forces. That's very different from an inorganic salt where it's purely an ion-ion interaction. Also, because those nonpolar tails are going to segregate themselves from the ions, we're going to get these nonpolar versus polar regions that are in this ionic liquid. And so that's going to complicate the structure a little bit compared to a typical inorganic salt that we could almost think of as one big polar region. Okay, so a lot of times when we talk about ionic liquids, it's useful to group them into what we call families. And members of one ionic liquid family are going to have a few things in common. First of all, they're going to have the exact same anion. Secondly, they're going to have the same cation, but that cation can have an alkyl chain that varies in length. So an ionic liquid family might look something like this, where we see, once again, we have those same anions, and the general structure of the cation is the same, but we're either lengthening or shortening that alkyl chain. That means that with the different alkyl chain lengths, we're going to have different van der Waals interactions in each of these ionic liquids. So although intermolecular forces are going to be similar in an ionic liquid family, they're also going to have slight variances within a family. So what are ionic liquids useful for? You can imagine that there's a lot of different cation and anion combinations that are going to yield an ionic liquid. And the variety of combinations that we have gives them pretty tunable properties, and it lends them to a wide variety of applications. Some of those applications include energy storage, such as batteries, and this is because ionic liquids are also pretty conductive materials usually. They're also being investigated as alternatives to aqueous amine solutions in industrial CO2 capture. And they're also being used as alternatives to traditional organic solvents and are often viewed as green alternatives to these more traditional solvents because they have negligible vapor pressures. So that means that they're going to typically be more recyclable than traditional organic solvents, and they're not going to evaporate at high temperatures. So if they're non-volatile, and if they're so great with all of these eco-friendly properties, then why don't we see them applied everywhere? And one of the main answers to that question is ionic liquids have viscosities that are really hard to predict based on their molecular structures. And this really does impact how practically applicable they are, especially in industrial settings. So if we think about what it would take to bring an ionic liquid to an industrial setting, let's consider a situation where we want to use an ionic liquid as a solvent for some organic reaction. We'll probably have a reaction canister that looks something like this, and we'll need to be able to do a couple key things with our ionic liquid. First of all, we will need to pump that ionic liquid in and out of the canister. We'll also need to stir that at reaction temperature, whatever that reaction temperature may be. And both of those procedures require knowledge about the ionic liquid's viscosity and how that viscosity changes with temperature. And so now, when we want to figure this out, we'll usually just go into the laboratory and measure these viscosities manually. So there's a lot of different ways to measure viscosity, but one of the most common ways to measure viscosity is called the falling ball method that's shown here. So what you do in this method is you essentially fill this tube with a liquid that you're interested in measuring, and you time how long it takes a ball to fall from one end of the tube to the other. How long it takes will depend on the viscosity of the material in the tube. You can imagine that this ball will fall much faster through something like water than it would through something much thicker and much more viscous like honey. But you might also start thinking that if we have to do this for every ionic liquid that we're interested in for a particular application at all of the temperatures that we're interested in, that's a lot of work. And for industries, that's an expensive, time-consuming project for an alternative that has somewhat limited benefits to them if they have to go through this process. And so to make these ionic liquids really applicable in especially industrial settings, we need to have more predictability based on their molecular properties. Okay, so how is ionic liquid viscosity currently modeled? If we need better prediction power, then what are we using right now? Typically, we'll go into the lab and take the data, and then we will fit that data with polynomials. And polynomials are great at fitting data, but they have been shown to be pretty poor at predicting viscosities of ionic liquids that haven't already been measured in the lab, especially if those ionic liquids have very different structures or intermolecular forces than the ones that had been previously studied. These polynomial fits also don't tell us anything about the intermolecular forces, which really determine viscosity. Which leads us to question, how valuable are these models in helping us predict the viscosities of ionic liquids? We want something that's going to get to the root of viscosity and tell us more about our systems and what's going on in them. And so alternatively, how does the CAF, or the compensated Arrhenius formalism, model viscosity? Well, the CAF says that transport is a thermally activated process. And when I say that, I really want you to be thinking about a picture that looks something like this, where we have energy on the y-axis and transition coordinate on the x. So as you can see, we have an initial and a final state represented by states 1 and 3. And we also have a transition state, state 2, that's higher in energy than those other two states. So applying this to transport in our ionic liquids, let's think about what a cation is doing in our liquid. Well, that cation is probably going to be surrounded by anions because they're allowed to form those those stabilizing Coulombic interactions. So now we're at stage 1. This is our initial state. But if we want to move that cation somewhere else into solution, how do we do that? Well, we have to go through this transition state. First of all, we have to break those intermolecular interactions. Then we have to allow for a slight expansion of those anions so that our cation has room to move. We're now at the transition state, where we have put energy into our system to break those stabilizing interactions, and then our cation has moved. Coming down from that transition state, we can imagine those anions reorganizing themselves around the cation, and then reforming those wonderful Coulombic interactions that are going to bring us back down in energy to our final state, state 3. You might notice that states 1 and 3, our initial and our final state, are actually pretty similar. If you look at the picture and if you look at the energy levels, they're actually really similar, even identical. And so the real keys to understanding transport is going to lie in this activation energy. How much energy does it take to actually cause this transport to occur? To think about that, we need to consider what affects an ionic liquid's activation energy. In short, intermolecular forces are going to determine this activation energy. We can think about what this picture might look like for ionic liquids that have either a strong intermolecular forces or weak intermolecular forces. The strong intermolecular force situation will probably have a high activation energy because more energy input is required to break those interactions and allow for that cation or that anion to move through the ionic liquid. We can also think about the weak intermolecular forces as being easier to overcome, and we need less energy input into our system in order to get from state 1 to state 3. These intermolecular forces are ultimately determined by the ionic liquid structure, as well as something called dipole density. And dipole density is equal to the number of positive and negative pairs, or the number of dipoles, per unit volume. So what affects dipole density? Well, to start with, the length of the cation alkyl chain will affect the dipole density. So let's think about having a beaker full of our ionic liquid to start with. And then if we choose to increase the alkyl chain length on our cation, our blue molecules, we can picture this new situation where we have increased the amount of volume that that cation is taking up, but we haven't changed the number of dipoles. We still have the same number of ions, but our volume has changed. And so in this case, we're going to have a higher dipole density when our alkyl chain is shorter and a lower dipole density when our alkyl chain is longer, because that alkyl chain, which isn't contributing to the dipole count, is going to be increasing the volume. But we also need to account for the fact that dipole density is temperature dependent. And this is something that other models ignore, but the CAF says that it's significant enough for us to include in our model of viscosity. So let's think about this picture of our beaker full of ionic liquids once again, and think about how that picture might change if we increase the temperature. Well, we know that liquids in general will expand when they're heated up, and ionic liquids are no different. We see that there's a thermal expansion of the liquid that causes our volume to increase. But once again, we haven't changed the number of dipoles present, so our dipole density is going to decrease. This means that our dipole density is going to decrease as we increase temperature. So then the question is, does the data suggest that this is a significant effect? To answer this question, we can plot dipole density against temperature. And each of these lines that you see represents an ionic liquid that's part of one family. So we can see that we fit the data with a linear regression line, and our R-squared values are close to 1. That suggests that we have a good linear fit. But the most important part of this plot that I would like you to notice is the fact that all of these trend downwards. So our dipole density is decreasing with temperature. And the CAF says that yes, this is a significant effect, and we need to account for it when we're trying to model ionic liquid viscosity. So to summarize this section of the talk, we essentially have two ways to change our dipole density. And the CAF is going to use both of these variables to identify how each affects the dipole density and therefore the viscosity. So Allison likes to call this a function box. And if we think about this idea of a dipole density, we can think about it as turning two knobs to affect the value of our dipole density. If we increase the temperature or we increase the alkyl chain length, we're going to decrease our dipole density. Alternatively, we can decrease our temperature or decrease our alkyl chain length, and that's going to increase our dipole density. What's important is that we can turn these knobs together to get a larger effect, or we can isolate them to determine the direct relationship between that variable and dipole density for that particular ionic liquid. Okay, so I've taken you through sort of the basics of CAF, but what data do we actually start with when we come out of the lab? And usually we're going to start with this plot of fluidity against temperature. Fluidity is 1 over viscosity, so we would expect it to have the opposite trend of viscosity in relation to temperature. So fluidity is how readily a material flows. And so if we heat something up, we would expect it to flow more easily. And that's exactly what we see here. However, this trend is pretty curved. And for understanding what's physically going on in this system and for predicting other ionic liquid viscosities, we would prefer something that's linear. And so that's going to be one of the goals of the CAF. So how does the CAF start to look at this ionic liquid data? We'll usually start with a plot like this, where once again we have fluidity on the y-axis, but instead of temperature, we have dipole density divided by temperature on the x-axis. Each of the different icons in the plot is going to represent a different temperature at which the data was taken. And we actually have 3 family members represented here. So this is essentially all of the data that we would collect in the laboratory for a single ionic liquid family. So looking at this chart, we can see how turning that temperature knob is going to affect the fluidity. For this, we'll want to leave that alkyl chain length knob alone, and we'll want to isolate how temperature affects the fluidity. To do this, we'll have to look at how temperature affects each of the ionic liquid family members by themselves. And that's represented, that data is represented by these lines here, where each line is one ionic liquid family member. But we can also think about turning that alkyl chain length knob by itself as well. And for that, we'll need to look at data from all 3 family members as we're adjusting how many carbons we have attached. But our temperature is going to want to stay constant. And so we're going to leave that knob alone. And that data is represented by these pink lines, where those pink lines are all of constant temperature, but each one varies. So this is really a key plot for us when we're starting to look at new data, because it can give us really important clues towards how temperature and alkyl chain length are going to affect fluidity. So how does the CAF use this raw data? First, we're going to perform a scaling procedure to obtain something called the CAF equation. And then we're going to get that activation energy that we talked about earlier. So we start with this equation where we have fluidity on the left equal to some fluidity prefactor times an exponential function to the power of negative EA over RT. The problem is that we know fluidity and we know RT, but we don't know what the value of that fluidity prefactor is. So to solve for our activation energy, we need to get rid of that fluidity prefactor. And the way we do that is we divide the whole equation by that same equation taken at a reference temperature. And we suppose, or we hypothesize that that fluidity prefactor is going to be approximately the same, so we can cancel it out. That actually turns out to be a really good approximation that we can check after we've completed our calculations. Okay, so once we've done this cancellation procedure, we can rearrange our equation into something that looks like this. And if you look at this long enough, you might realize that this looks like a linear relationship, where our y value is the natural log of our scaled fluidity, and that's equal to negative EA over R, that's our slope, times 1 over T, our x value, plus EA over RT, and that's the temperature at which the reference was taken. That's going to be our y-intercept. So if you notice, we can get the activation energy from either the slope or the y-intercept. That's going to be a great self-check for this method, because if those two values don't match up, we've done something wrong. Okay, so does that equation actually linearize the data? If we have fluidity data and we put it into this equation, does it actually work? And to answer that, we make something called the compensated Arrhenius plot, which is based on that equation that we just went over. We have the natural log of the scaled fluidity on the y-axis and 1 over temperature on the x-axis. Once again, we have our 3 family members represented here, each one with its own regression line, its own slope, and its own y-intercept. We can look at the r-squared values on this, and we notice that they're very close to 1, which suggests that this is a good linear fit. And like I said before, we can extract activation energies from the slopes of these regression lines, as well as the y-intercepts of these regression lines. And so we determine an activation energy for each of those family members. Then what we can do is we can calculate an average activation energy of the entire ionic liquid family. You'll probably notice that these activation energies are pretty similar to each other. And that makes sense because we would expect those intermolecular forces within a family to be quite similar, though not identical. So what do we do once we have the activation energy? We actually go back and solve for that fluidity prefactor that we canceled out before. So we go back to this equation, and if we solve for that fluidity prefactor, we see that it's equal to the fluidity, which we have data on, over this exponential function. But now we can plug in that activation energy that we just solved for and find a value for our fluidity prefactor. This fluidity prefactor has been related to ionic liquid structure and entropy. So it's going to be a key part of how we're learning about these ionic liquid systems. So what do the fluidity prefactors look like within an ionic liquid family? Well, what we do is we relate these fluidity prefactors of each ionic liquid family member to get a similar overall trend, which I'm going to call a master curve. So once again, we have our 3 family members, all plotted with their fluidity prefactor against dipole density. And as we see, they all follow a similar trend. That's good news because we would expect that. Similar structures and entropies should yield similar prefactors. And so it's a good sign that we're seeing this master curve within an ionic liquid family. So once we saw these plots, the question that we were interested in answering next was, can we get a master curve with multiple ionic liquid families? So can we see that all ionic liquids perhaps fall on one master curve, or do they deviate slightly? And so to investigate this, this question, we looked at 8 ionic liquid families with the CAF. We took 5 from Allison's data, but we also looked at 3 families from the literature. And we had a couple of reasons for being interested in the literature. First of all, it allowed us to expand the types of ionic liquid families that we could look at. Some of them were difficult to synthesize, but if we could get the data from the literature, that it was a nice way to get at some weirder structures. But also, we wanted to look into the literature because if the CAF is really a good model, then it should be able to help us explain any data that we throw at it. And so this was a way of putting the CAF through a really rigorous test. Okay, so we are back to questioning, how do these ionic liquid families and their prefactors compare? So we made this plot where we plot fluidity prefactor against dipole density. And each of these different colors represents a different ionic liquid family. So I hope that something is striking you, as it struck me when we first made this plot. And I hope that that is the fact that we see 2 distinct groups in this plot. The blue group, which looks like it seems to have a very high dependence on dipole density in the fluidity prefactor, versus the yellow group, which seems to have a more moderate dependence on dipole density. So after we saw this, we immediately started thinking about what's causing this. And to start answering that question, we have to think about how the ionic liquids in each group compare. So we have the blue group, and in that group, we tended to see more localized cationic charges. So what I mean by that is we saw more positive charges residing on a single atom, as opposed to being delocalized through some sort of ring system. The blue group also tended to have higher activation energy values on average, and they showed more deviations from linearity in the plot of fluidity prefactor versus dipole density. That might suggest that their intermolecular forces have a more complex relationship with temperature than the other group. So in the yellow group, we tended to see more delocalized cationic charges, so a lot of imidazolium rings, things like that. We also saw lower activation energy values and very linear behavior in the fluidity versus dipole density plot. So while these 2 groups did have a few differences, we noted some important similarities. The first of those is that they had similar anions, and so we can't attribute this difference in behavior to some difference in anionic structure. They also tended to have comparable hydrogen bonding capabilities. This is something that we would really like to investigate further because, once again, we have 8 ionic liquid families, but having more can give us a better idea of how these hydrogen bonding compares. Okay, so why is this plot so interesting? Why do I keep talking about it, this plot with the 2 groups? First of all, I think it's interesting because we didn't expect to see this. We thought initially that we might get one master curve, which would have been cool, but this is so much cooler because it's telling us that we don't understand something yet. And we stand to learn something about these ionic liquid systems that we haven't learned yet. I think it's also interesting because it's a purely CAF plot. You would not see a plot like this anywhere in the literature analysis today, because the fluidity prefactor is a purely CAF plot. And I think that that's interesting because the CAF is really teaching us something here, and it's really showing us its power. So this plot can also possibly teach us about the intermolecular forces that determine viscosity, and maybe even perhaps how the nonpolar and polar segregations in ionic liquids are causing more complex relationships that are affecting viscosity. So what does this mean? I have showed you a lot of data, I've shown you a lot of pictures, but what I really want you to walk away with is the idea that the CAF is a powerful tool for revealing relationships in ionic liquid data that we would otherwise miss. That plot that has the two groups is something that we only found because we used the CAF. Also, there's way more to investigate. So these are the ionic liquids that belong to each group, where the blue is the high dependence group and the yellow is the moderate dependence. So we would like to look into the specifics of these structures to see if we can see any differences in their structures that might explain their difference in behaviors. Another interesting thing to note is that the ionic liquids that are boxed in white are the ionic liquids that we got data from the literature on. And so we may have been concerned earlier if all of these were to fall into one group, we might be worried that there's some sort of data bias that was causing that difference. But since we see literature values in both groups, we're more inclined to think that this is a fundamental difference in the ionic liquid structures and their behaviors, and not a data bias. So there's more to investigate as we learn about these specific ionic liquid systems and as we look forward to investigating more ionic liquid families. So then, where to next? First of all, we would like to analyze CO2-rich ionic liquid samples and compare their viscosity temperature relationships to that of their pure form. So adding CO2 to an ionic liquid actually really changes the intermolecular forces that are happening in that liquid. And so that could be a really cool way of investigating how intermolecular forces are tied to viscosity. It would also be a great research project because it could contribute to a conversation on how applicable ionic liquids are in the CO2 capture area. We would also like to analyze new ionic liquid families. We've analyzed 8 here, but in reality, we would like to have a much broader view of these ionic liquid families so that we can say something more concrete about what's causing these differences. We'd also like to, of course, explain the origin of those two groups that we found in this investigation so that we can learn something about our ionic liquid systems. And finally, we would like to do the same analysis with conductivity. So the CAF also works with conductivity, and we were wondering that if you do that same analysis, if we would still see the two groups that formed in the prefactor versus dipole plot. So here are my references. They were all wonderful references, so check them out. And I would like to thank, first of all, the Thomas A. Stites Nobel Fund for funding this research. Of course, Dr. Alison Fleischman for her support and guidance and inspiration throughout this process. Dr. Stefan Debert for all of the advising that he's done for me and helped me with throughout the years at Lawrence. The chemistry faculty and my fellow senior chemistry classmates. Thank you all for your encouragement. And of course, I would like to thank my dogs, pictured here, Cody and Sam, for their emotional support these past few weeks.
Thank you so much, Katie, for the talk. I think Katie is very willing to accept questions. So many ways to submit a question. It's hard for me to scroll through you all. So if you have a question, you can sort of unmute yourself. If you want me to call on you, you can raise your hand in the participant section. Or if you want Katie to call on you, we can try to catch it. But open the floor for questions. So I guess I will start with a question. I think in particular, do you have any idea of what ionic liquid you would like to try next to see if it fits into one or the other categories? That sort of gets to the point of, do you have any ideas of what is causing it at all?
Yes, yes. So that actually ties into some of Evan's research, looking at, we've ordered this ionic liquid family that one of them has pretty strong hydrogen bonding and the other one doesn't have very strong hydrogen bonding. And so we'd like to analyze those and see if hydrogen bonding is still sort of in the running as we look at the cause of that.
And thinking about their applications for carbon capture, do you have a sense of how expensive these are relative to other ways of doing carbon capture?
So I think that's a complicated question. I think it's a fantastic question because it's practical. But so traditionally, aqueous amine solutions have been used in CO2 capture. But the problem with those is that they degrade rather quickly. And so they don't have as much recyclability as ionic liquids have shown. And so ionic liquids have more of an upfront investment, but they would be more recyclable and more reusable, so they would last longer. So I think it's a complicated question, but I think it would really depend on, you know, like upfront cost versus maintenance cost. And I think part of it too is how viscous is your material? Because if you have to transport and stir a more viscous material, well, that takes more energy and that's more expensive as well. So I think there's a lot of variables, but I think that they could potentially be a cheaper solution.
I have a question. Do we always think of viscosity as a macroscopic property, or can we think of it as a more microscopic, since you have all those polar and non-polar domains within the ionic liquid? Can you have like a more viscous zone with, and then a less viscous part of your liquid?
That is a fantastic question. And I think that when I think about the CAF versus other models, I think that that's really where my mind draws the line, where the CAF is looking at the very small scale interactions, right? One molecule talking to the other molecules around it. Whereas other models, you know, they use, a lot of them use hydrodynamic theory. And so I think it depends on what model you're talking about. You can look at viscosity in a lot of different ways, but I would say that the CAF tends to look at it as more of a small scale interaction. Yeah.
Other questions?
I have a follow-up question. So it looks like, so you're essentially trying to figure out how like viscosity is determined by all these like molecular properties of these liquids, and you're taking data and from there you're extrapolating some sort of trend within this data. Could you think, or would you think it'd be a good approach to do this computationally, where you could input a bunch of variables and then just see if your computations give you some similar, maybe just comparing to your CAF predictions, or just, I don't know, just seeing some other approach onto this problem?
I think the short answer is absolutely. I think that that would be really cool. Yeah, I think that's all I got on that one.
I can chime in on that one. So that was actually what I tried to do for my master's. And the way that so the way that Katie showed the dipole density and how it changes as a function of temperature, in order to do that, to model that computationally, it was quite this was 10, 12 years ago. 12 years ago. Oh God. Anyway, but it was so expensive computationally to take into account that dipole density that we couldn't, the calculations took like 6 months, and then there would normally be some small thing that would fail. So today I'd love to try that if we had like a supercomputer to look at a small box of molecules that we would repeat. But to get those two things to come together, so like Katie's data from the literature and from my own, and then a computational study would be the icing on the cake, I think.
Any other questions? I don't see anything. So I guess let's thank Katie one more time for an excellent talk, and I thank you all for joining us here. And I hope to see you all next week with 5 more talks that will start on Wednesday at noon, as Winifred Waters gives her talk, and continue on Wednesday afternoon, and then Friday afternoon with even more. So all sorts of fun next week, and I hope to see you there. And if you would like to stay and ask Katie questions or tell her congratulations, feel free to stay for the next little bit. We will be here. That's all. Thank you. Bye-bye.
Congrats. Good job.
Job.
Good work.
Yay.
Guys.
Good job.
All right.
Wait, Deanna,
Mm-hmm.
isn't my talk on Tuesday instead of Wednesday?
Wednesday. I was worried I said Wednesday. It is on Tuesday at noon. I'm sorry.
Okay,
Cool hug.
Wanted to confirm. Thank you. Bye. Good job, Katie.
Bye, thanks for coming.
Go team, virtual hug.
Thank you guys for all your help.
I texted Deanna during the whole thing and I said, this is the best description of a CAF I've seen from a student. No, seriously, the function box. So awesome. Go team. It went beautifully. Good job. And congratulations. We normally would award you with the senior award at the honors dinner, but there won't be one. So I don't know how you'll get your award, but ta-da.
Well, thank you. That was a nice little surprise.
You've done all the work. It's really, thank you. Like it's one of the fun parts of our job is to get to select a student. And it was really funny too, because in our department meeting, it's like, okay, the awards, senior, Katie. Yep. That's how it was decided. So
usually we have more of a debate.
there's normally like 2 or 3 that were like, well. So go team.
Couldn't have done it without you guys.
I
Yay.
hope you weren't offended by me muting. You're just like a little bit choppy with the video on, so I hope that didn't throw you off at all when I turned it off.
No, honestly, I just I don't know, minimized the video one. So yeah. But
So.
thank you.
Sweet.
And then your audio came through very clearly, and it was good.
Okay, awesome.
Awesome. We'll go celebrate, take the night off. You've done such a fantastic job. So go team.
Thank you guys.
Do you want me to end the meeting? Did anybody else have anything to say?
Okay, there we go. I was like, oh.
How are you?
Good. How are you doing?
Good. I have I don't know. I don't know. That's how I am. I don't know. By the way,
I have some.
Get a chance to say that I think Evan's talk really improved from when I saw it. So I don't know how much work you put in with him or what he did on his own, but it was not the train wreck that I had first saw. It wasn't bad.
Cool. Yeah, I had to pick my battles on that one. But I respect that these are adults, and if they want to do the work, they will, and if they don't want to do the work, you have no.
Yeah, but it wasn't like, I think the first time I saw it, you were like, oh no, that's wrong. Oh no, that's wrong. By the way, Carl gave me his, and I was like, yesterday I spent 2 hours with Carl because it was so bad. So.
Yeah, he didn't. He didn't do so well on his PChem exam either. So.
I mean,
but Interesting thing. So, PChem exam.
Oh my God, we're still recording.